All right, hey everyone. So today we're going to be doing our quick introduction to machine learning in R. So there's going to be a lot of new terminology and a lot of new kind of coding today, coding syntax. So it's going to go fairly quickly. You might not get it all in the first watch. Rewatch it if you need to. And this is, of course, for your interest. This is not going to be tested on the final exam. So what packages are we going to need? We're going to need some new ones. We're going to need these two, Caret and ML Bench. Tidyverse is always nice to have, so we're going to have that too. Now, I mentioned in the lecture that we're going to be doing two kinds of supervised learning. There's the regression kinds, which is similar to our OLS, our LM model. And then there's the classification kinds of supervised learning, where we're trying to predict which category a particular observation will fall into. So let's start with regression. So we'll load up our libraries. And the problem that we're going to be looking at today for the regression is going to be predicting home prices. So the data set we'll use is preloaded as part of the ML Bench library. And it's Boston housing prices from back in the day, I think from the 70s or 80s. It's a good data set for kind of benchmarking the performance of machine learning models. That's kind of what it's here for. So when we run this command, we'll see in the upper right, Boston housing appears. And one thing about machine learning models is that they don't like incomplete data. So we're going to use filter to go from our 506 observations. We'll only take the complete cases. And we still have 506 observations. Very good. That's why this is the benchmarking data set. It's complete. So just checking that, that's all good. We'll take a look at the data. What we have are a bunch of numeric variables, CRIM, ZN. The thing that we want to be predicting, the variable we want to predict, our Y, is median value, MEDV. So the median value in thousands of dollars of a house in one of these Boston kind of sub-neighborhoods. So there's 506 neighborhoods, and each observation is the median value of a house in one of those neighborhoods. Okay, so that's what we want to predict, housing values. We have the data, we have some variables, so let's get to it. Remember, the first thing with machine learning that we need to do is create training data and testing data. So for training data, what we're going to be doing is creating an index of row numbers that's going to be in our training data, and then we'll take the inverse of those for our testing data. So to get to these row numbers, we're going to use the command from Caret called create data partition. Create data partition means we're going to create a training data partition of our main data and then a testing data partition. So what's required? We can see in this pop-up, it needs Y, so it needs our dependent variable. So this is new notation to access a variable from a data set that we have loaded in memory. We can use this $sign. So we use data, set name, $sign, variable name. Right? If we just run this, Boston housing, $sign MEDV, we just see this is all of the housing values in our data set. So it needs Y, it needs P. P is the share of the data set that's going to be used in our training data. And it also wants this list equals false. So that we don't have a list of indexes, we just have a vector of indexes. So how does this work? It basically takes a random sample of half of the data and says that's going to be our training data. Now you might be wondering, okay, that sounds good, but if I run this code again, will I get the same sample of training data? And the answer is no, because it's randomly selected, right? You might get a different randomly selected half of the data. And that's not good if we want to reproduce our code and be able to kind of go through it and get exactly the same numbers each time. So what we'll do is we'll use this command setSeed. which if we set seed before we run something random, then we're going to get the exact same random result each time, because a computer can't generate true random numbers, only quasi-random numbers, and set seed will make sure that those quasi-random numbers are the same each time we try to sort of run through our full code to check that our results are replicating. So we're going to have two data sets, training and testing. In train is a vector of 124. We can see up here in the upper right. It's a vector of 124 indexes, row numbers. So here's a bit of new notation as well. We take our data type, our data frame, Boston Housing, and we can take the subset given by these row numbers. Okay, so if we run this, you'll see that we'll have a new data table called training, which is 254 observations, the same length as our index, and every single number in this in-train index is going to be a row that gets pulled from the Boston Housing data set. Okay. Everything that's not training data is going to be testing data. So we're going to use the negative of in-train. This is an R convention where if you take the negative of an index, it's going to say, okay, you want me to keep everything but those things that you've specified with the negative in front. So that's perfect. That's just what we want. And testing data will form kind of the other 252 observations in our data, right? So about an even split, that's what we were looking for. We have our training data. Are we ready to actually run the model? Not quite yet. So what we need to do first is pre-process the data. Okay, so machine learning models typically don't like data that's not centered at 0 and with a normalized coefficient or normalized standard deviation. So it's explained a bit in the Stock and Watson book, in the chapter on big data and machine learning. So you can take a look at that if you're curious, why do we have to do this? But what we will be doing is taking each random variable, finding its mean, and then subtracting that mean, and then dividing by the standard deviation of each variable. So it's a kind of a normalization. It's centering it and it's scaling it. Okay. So we'll use this command preprocess on our training data. Now, the only thing we want to preprocess are our X variables. So medv, we can see in the upper right, we have 14 variables in Boston Housing. Medv is the 14th. So pre-process, we want to apply to everything but the 14th column. All right, so that's that. And for method, we're going to want to center it, and we're going to want to scale it like I described. So center means they're all going to have a mean of 0, and scale means they're all going to have a standard deviation of 1 in the end. Okay, so this is our pre-processing model. And now our kind of, we'll call it training 2, will be our sort of pre-processed training data. So we'll need to put back in our outcome variable, medv. And then we need to use the predict command using our pre-process model and our training data dropping medv. Okay. And this should not be Boston Housing. This should be training data, right? We want to put back in our training outcome variable. All right, so now we have training 2. Okay. And looks like I made a small error here. We want this to be just medv, not training.medv. So we'll need to assign it a variable name like so. And now we're good. Okay, and you can kind of see, we compare training 2 to just training. So training, we have crime values that are all positive, this first column here. Training 2, some of them are negative, okay? If we take the average values of, say, now I'm in the console, training, take the average value of crime, it's 4.286. take the average value for training 2, it's basically 0, right? And this is a value that's very, very, very small, basically equal to 0. So, just kind of numeric overflow errors in the computer's sort of ability to process really small numbers. It's basically 0. Okay, so we've centered our variables and we've scaled them. Scaling them, what does that mean? We take the standard deviation of prime. In the base, it's 9.856. We take the standard deviation in training 2. It's 1. It's gonna be the same for all of the x variables. They're all gonna be mean of 0, standard deviation of 1. That doesn't mean they're all identical, right? Each one is taking different values. But this is kind of within each variable, we're kind of shifting it to the left and kind of squishing it a little bit, okay? Or expanding it, as the case may be. And now we're actually ready to start running models, okay? So we're going to start with our friends, the linear regression model. So train is the command. So into train, what we want to feed is a formula, right? Just like our regression formulas. We want our y variable. And now for x variables, this will almost always be the case that in machine learning models, we'll just throw in every single x variable that we have. So how do we do that in an easy way? We can just include a dot, okay? This is saying regress, or our model will be medv, our y variable, as a function of every single thing in every single other thing, all the other 13 variables in our data set, okay? So our data will be training 2, and our method will be lm, okay? Perfect. Now for the linear regression model, this is it. So we can run it. And you'll see, okay, now we have this thing that's appeared. What does a machine learning model look like? Well, let's just look at lmfit. It says linear regression, no pre-processing. We already did all our pre-processing. And we have a root mean squared error, 5.45. We have an R squared of 0.76 or 0.67, mean average error, right? So here's kind of what the machine learning algorithm cares about: our accuracy, right? Our performance in terms of prediction accuracy. Okay, so that's our LM. And of course, with machine learning, what we want to be able to do is compare models, right? Which model is performing the best? So let's consider some other models. So we talked about the k-nearest neighbor model in class. So KNN. So where am I getting these method things from? So I'll provide a link, but there's over 200 different machine learning techniques that are implemented as part of this train function, okay, including old stuff up to the most recent stuff. So you can look up that list to find lists of all the different options. Most of it will look very complex. It's implemented very easily here, but you typically shouldn't use something that you don't know exactly like what it's doing or why it's doing it. Having said that, I will show you some techniques that I haven't explained how they work. Okay, so with k-nearest neighbors, we know that only have one nearest neighbor, 2 nearest neighbors, 6 nearest neighbors. How many nearest neighbors should we be picking? We'll have very different predicted y's depending on what we pick. Is it up to us to pick? No. So the number of nearest neighbors is a parameter that we can choose through that kind of k-fold cross-validation procedure that I described for the lasso. We can also use it here. So what do we need to specify? So we need to specify some additional control parameters, okay? So the control parameters, we want to do repeated cross-validation, okay? So we'll have method equals repeated CV, and then the number will have 10-fold cross-validation. Remember what that means is we take the training data, we split it into 10 chunklets, and then we fit the model on 9 of the chunklets and then use the first chunk to test it, right? And to test the kind of out of sample predictive accuracy. And then we repeat that 10 times. We take the average of those out of sample prediction accuracies. And then that will kind of tell us, okay, for a particular value of the nearest neighbors parameter, right? 1 nearest neighbor, 2 nearest neighbor, how well is our model performing? And so we can do that k-fold cross-validation for different values of the k nearest neighbors. And that's going to lead to, allow us to pick which of the k nearest neighbors is kind of the right one. And all the code in the background will do that for us. The only other thing we need to specify is how many values of k do we want to try, right? For the k nearest neighbors, how many, 1 nearest neighbor, 2 nearest neighbor, 5 nearest neighbor. So we're going to have 15 different values being assessed. Okay, and we'll run knn fit, and that's run as well. So now we can take a look at knn fit. And here we can see for all the different k values that it's tried. So it's tried 5, 7, 9. So it looks like it's trying kind of odd values from 5 up to 33. And we can see that the root mean squared error is kind of continuously increasing. The R squared is continuously decreasing. So the best performance is coming from k equals 5. So that's going to be what the model uses, or what the algorithm uses to select our k nearest neighbors. So it's going to use the 5 nearest neighbors. And it did that through this cross-validation procedure. Okay, perfect. So now we have a second model, and we could compare these two, but let's do a few more models. I mentioned the lasso. So let's train the lasso up. Okay, and for this, I need to remember exactly what is the lasso. I think it's method equals lasso. Yeah, it's method equals lasso. Very good. And again, so the lasso has a parameter that needs to be kind of tuned, which is that kind of weighting parameter on the portion of the objective function that's like the shrinkage, right? That we're trying to shrink the coefficients towards 0. So our shrinkage parameter, again, we'll use repeated cross-validation. We'll do 10-fold cross-validation, and we'll try out 15 different values of that shrinkage parameter. Okay, now we fit the lasso. Let's take a look at that. So here's kind of the different kind of shrinkage parameters that are being tried out, and our root mean squared error is continuously decreasing, right? So we'll be using this as kind of our final value for the shrinkage parameter. Okay, 0.9. If we were using, yeah, okay, yeah. So that's what we'll be using. Okay. And lastly, use what's called a support vector machine, SVM, which is kind of more modern. People don't like the lasso as much anymore. Support vector machines are kind of the better performing model. So we'll use SVM. And this is the name of the machine learning algorithm, SVM Radial. And once again, we'll allow tuning of, now for SVM, I haven't told you, what is this? How does it work? And this kind of shows you both the power and the danger of machine learning. You can just say, okay, this is the newest, best thing. All right, let's just run it and see what happens. Don't really know how it works. Maybe it'll work the best, not sure. But we can run it very, very easily. Okay. And yeah, so I don't think that it's wise to present results from models that you don't know how they're working. So I'm going to kind of be doing it today. But in general, it's just kind of this is sort of meant to be sort of a cautionary lesson. Like, I think SVM will end up performing very well. But why? That's something that we should understand. Okay. Because there could be follow-on questions, and it's just good to know how things are working. All right, so now we have our models. Now, how do we kind of assess them? So remember, to assess the models, we kind of want to be using the root mean squared error. So what we're going to be doing is we're going to be using sort of this function called resamples in order to summarize. So resamples, we're going to list out all the models we've done and kind of name them. So linear model, that's LM fit. KNN, that's our KNN fit. Lasso, it's lasso fit. Support vector machine, it's SVM fit. Okay. And we'll name this models compare. And then we'll do a summary of models compare. Okay, all of this is new. There's no reason for you guys to believe, like, why does summary operate in this different way? Like, I know I can summarize regressions, but why is it working here? That's something that, you know, is new to you, right? Summary in R can summarize a lot of different things. One of the things it happens to be able to summarize is a list of different models, okay? Oh, so I think for the purpose of this resample, we do need to have had done cross-validation with our linear model, which isn't super meaningful in the sense that it's actually not choosing a parameter when it's doing the cross-validation, because we know the linear model, there is no parameter, there's no number of nearest neighbors, and there's no shrinkage parameter. But we do need it to have done kind of repeated resampling so that when we do our models compare, okay, here's what we have. Now let me kind of explain what's going on. So we see three kind of sets of results, MAE, RMSE, R squared. Let's look at the root mean squared error. And then we can see we have our four models that we've named in this models compare list: LM, linear model, k-nearest neighbor, lasso, and support vector machine. And what we can see is for our root mean squared error, we want the model that's performing the best. We want the one with the lowest root mean squared error. And we can see that LM performs the worst. K-nearest neighbors seems to perform okay. Lasso performs badly, but not as badly as LM, as the linear model. And then our support vector machine performs the best in terms of smallest root mean squared error. Okay, so this chart, what are all these other things? These are quantiles of the distribution of the root mean squared errors calculated under different samples. Don't need to worry about that. Just need to worry about this mean performance. Okay, and it's our SVM that performs the best. Why does SVM perform the best? Well, it's designed to perform the best. It's the newest. It is the most robust. But how does it perform the best? That I leave to you guys if you're interested in learning more about it. Okay. I didn't even show, you can run a neural network just as easily as anything else here. So if you want to say, yeah, I've run like a neural network analysis on like some training data, then you can totally do that. Just look up for the Caret library, look up, okay, what's the kind of, I'll have a link for all the models that are available. And you can look up, okay, how would I do a neural network, right? Just to be able to say that you've done a neural network, right? That's cool. It is cool. So let's look at the kind of one other piece of analysis you can do. Now, notice all of the output, there's no coefficients. There's none of the usual, there's no t-tests, none of the usual stuff that we care about for causal analysis. Is there any way to say what of these variables is kind of important for our predictions? There is. So you can use plot and then impvar, so important variables. And this is just like a command that is available alongside the Caret library. And we can plot our different, models. We can plot our different models. So let's see, what does that actually mean? So in the bottom right now, we have this table. On the x-axis, it says importance from 0 to 100. It's always going to be from 0 to 100. On the y-axis, we have the different variable names, RM, LSTAT, DIS, PT ratio, etc. Okay. The top variable will always be at 100 because all the other variables are scaled relative to that one. So you can kind of think of this as a measure of how important are the different variables in explaining the variation in the y variable that we see. And this says, okay, RM is the most important, and then LSTAT, DIS, PT ratio. So these ones are kind of progressively less important until we get all the way down to age, which is the least important, interestingly enough. Okay, so these are kind of measuring the importance of variables relative to each other in explaining the outcome y, right? So this is kind of one thing we do, and then we can kind of see with other models, right? So with the support vector machine, we can see that LSTAT and RM are still fairly important, but their order's kind of switched. And then this DIS actually drops way, way down. And age is no longer completely unimportant, right? So it's kind of picked out different variables as being important to explain the data, right? So that's kind of one last way to assess it. And then now, of course, what we want to do is predict well, right? And so we picked a model that can predict well. It's our support vector machine. So what predictions does it actually make, right? So we can use the test data for that. So in order to actually predict using our testing data, we need to pre-process it using the exact same pre-processing model as we used to create our training data, right? Because our training data is centered and scaled, and our testing data currently is not, okay? So how do we do this? What we need to do is use our create testing 2. Okay, so we're going to want our median value as before, right? And then for our kind of predicted values, or for our centered and scaled values, we're going to need to predict using the previous model, so the pre-processed model that was fitted on the training data, but we'll use it on the testing data, of course, dropping our outcome variable, right? And now we have testing data that has been kind of scaled in the exact same way as the training data. And we can predict using the testing data, just using the predict command. So let's look at using SVM fit. Here's our predictions on the test data for housing prices, okay? If you're making decisions about kind of like what would be the predicted value of houses, and so like which markets should I kind of focus on serving, or whatever your decision happens to be, you know, here they are, here's the predicted values, okay? So these predictions, once you've done all the steps of validating your model and kind of picking the best one, the predictions are now kind of the things that you care about. Versus with the causal analysis, right, once you've kind of estimated the model, it's the coefficients that you care about, and you're kind of interested in, you know, that increase or decrease in y from changing x. So very good. So this is our regression style, and now let's quickly do a classification style problem. Okay, so for classification style problems, we're going to have very, very similar syntax. So we're going to need to use a different data set. So I found a data set online, which is something I mentioned, I think in the lecture. So it's orange juice brand purchasing. Okay, so here's kind of a fun new thing that you can see. R can read data directly from URLs. So here's a URL, it's someone's GitHub. They have uploaded this orange juice data. Okay, so we can pull that data and use it ourselves as long as that link is active. So before we proceed, because I'm going to reuse a bunch of the same variable names, I'm just going to clear out everything. Okay, and so now I'll read in this orange data. We have 10,000 or 1,070 observations, and we can filter it. Okay, we've dropped about 38 observations. take a look at the orange. You can see purchase, week of purchase, store ID, price, et cetera, et cetera. Okay. Okay, purchase. I think MM is Minute Maid. CH is another brand of orange juice. It's just the two brands. So we have a category with a categorical variable with two categories in it. Okay. And we want to predict so given all this kind of data on consumer purchasing of these different brands, we want to predict, okay, for another consumer, what brand are they likely to pick, right? Which brand for which type of consumer, based on all these observable characteristics. Okay, so same deal. We're going to need to do our training or create our training data set. So let's grab create data partition. Our Y now is going to be orange, and then we're going to take purchase. P, let's do 0.5 again. And list is false. And so our training data is going to be orange with the indexes given by this training data split, this data partition, and our testing data given by the obverse. Okay, so now we have our testing and our training. Now this one's an even split for this orange juice data. All right, what was the next step? Next step is we need to pre-process. So for pre-processing, there's something a little bit new in the orange data. Most of this is numeric, but we do have one categorical variable, store 7. It says no and yes, right? So we could recode this by hand into 0, 1. Instead, we'll do it machine learning style, okay? So what are we gonna wanna do? We're gonna wanna do the same pre-processing we did before with the demeaning and the rescaling, but we're also going to want to recode our categorical variable as dummy variables. Okay, so the order in which we should do things is turn the dummy variables in, or turn the categorical variable into dummies first, then do the centering and the rescaling. Okay, so that means we're going to have an extra step in our pre-process. So we're going to have a dummies model, and the dummies model is going to use this dummy vars. And we'll have purchase. Our data is training data. Now for this one, we can just specify it as is. We don't need to drop the sort of the purchase column from the training data. Okay, and then we'll create training 2 is going to be equal to our predicted from the dummies model. We'll run, well, I'll say new data. Okay, and so that's our first kind of level of pre-processing. We've hopefully turned our dummy variables into we've turned our categorical variable hopefully into dummy variables. All right, so training 2. Okay, so this looks like it should be right. Yes, so now we have store 7 no and store 7 yes, right? So we've created these 2 dummy variables from our categorical variable of no yes, right? Perfect. And the next thing that we need to be doing is the pre-process for centering. So we'll have our pre-process model is going to be like above now. So we'll have pre-process, have it on training 2, and then we'll center and scale. And then because training 2, notice purchase has dropped out, right? So basically what that initial pre-processing did is it looked through the data, looked to see if there's any categorical variables, except for the outcome, right? Purchase. And then it turned categorical variables into dummy variables, and it returned that to us. Okay. And now we'll reinsert our purchase, our outcome variable. The purchase is equal to training, right, our original purchase values. And then we'll predict from the pre-process model using training 2 data. Okay. Perfect. And now we're done. Now we're good to go, right? I've got everything centered, scaled. Categorical variables have become dummy variables. So now we can start working with categorical models and start fitting our models. Our classic Logit is a great choice for a categorical model. So we'll do train, and we want purchase as a function of everything. Our data is our training 2. Our method is GLM, the generalized linear model that we have before. And like before, we also need to specify this kind of binomial family for the Logit. And with the Logit, there is no parameter to be tuned. Okay, so with no parameter to be tuned, we don't need to do this repeated cross-validation. However, if we do want to use that kind of resample function to assess our model performances against each other, we do need to have some kind of repeat sampling. So we'll specify this here. Okay, we'll have method equals repeated cross-validation, 10-fold cross-validation, and that's it. So that's our Logit. What other types of classification models are out there? There's a ton. So you can kind of just, again, and now these are going to be ones whose names are kind of very fancy sounding. I haven't explained to you how they work. So I would definitely encourage you guys to look it up. So let's just do, one. So it'll be the, let's see here, multivariate adaptive regression splines model. So that sounds really fun and fancy. So let's do the multivariate adaptive regression splines model. Okay. Multivariate adaptive regression splines, Mars. Purchase on whatever, data is training 2, method equals, and for some fun reason, the multivariate adaptive regression splines model is not Mars, it's Earth. And then everything else is as usual. Repeated cross-validation, 10-fold cross-validation, tune length, let's try 15 different values. We have, I don't know what the hyperparameter is, what the parameter like the shrinkage or the KNN is for this particular model. But I can specify, let's look for 15 different values of it, okay? And so when we run these two models, right, so it looks like the Logit threw some warnings at us, right? That's fine. Our multivariate adaptive regression splines, it took a little bit longer. That's fine too. Good, now we have our two models. So we can evaluate with models compare. How are they performing? And of course, yeah, naming them is always good. So we have our Logit for Logit fit and Mars for Mars fit. Now, again, we have these kind of subheadings with our lists of models. We have Logit and we have Mars. There is no more root mean squared error. Right? Like I said, with the classification models, you can't compute root mean squared error. Here, what we're computing is accuracy, which I mentioned in the lecture. It's like the percent correctly predicted. So our Logit predicts, on average, about 82% correctly. So if you're a Minute Maid person, then it'll predict. So if you're a Minute Maid person, it'll predict Minute Maid. And if you're a CH person, it'll predict CH. And in total, it'll be predicting correctly 82% of the time. So that means 18% of the time, it'll predict you're a Minute Maid person, even though in the data it says you like CH or you chose CH, and vice versa, okay? It looks like our MARS model performs a little bit better than the Logit on average, right? So we may want to select that. And we can still do things like gauge the importance. What was it, var imp or imp var? Var imp. Look at the importance of the various. Right, so this is the various variables. So loyal to CH seems to be the most important predictor for predicting whether or not you're going to be purchasing CH. That makes sense. If you're loyal to that brand, the prices also seem to matter a bit, okay, for the Logit. And for our Mars, so with Mars, it looks like it's a type of model that actually drops some variables, right? Just like the Lasso would do. And Mars seems to be kind of just selecting these first 6 variables, okay? But loyal like is the same. It's the same as Logit. It's kind of picking that out as the most important one. All right. So last thing, we want to predict. So in order to predict, we need to do the same to the testing data as we did to the training data. So that means we need to turn dummies or turn categories into dummies and rescale everything. Okay. So let's grab, so we're going to want to create something called testing2, where we use our dummies model to predict using our testing data. And then we're going to reuse that pre-processed model that we fit, and then testing2 is going to have purchase. It's going to use the purchase values from the testing data. And then we will predict using the pre-processed model. New data will be testing2. Right. Perfect. Once we've done that, then we can predict using our Logit fit and our new data. Or our Mars fit with our new data. And then here's our predictions, right? On that data, the testing data that we did not use to fit our model, we can see, okay, who are we predicting to consume the CH brand and who are we predicting to consume the Minute Maid brand, right? And then our Mars fit, we have the exact same kind of thing, right? Who do we predict to consume which brand? And that's kind of our output. So that was your very, very brief intro to the 2 kinds of supervised learning problem. We have the regression style, and then we have the classification style. So you can see that it's easy to do. It's very, very different than what we've been doing, right? The output looks totally different. We only care about this accuracy performance of the model. We don't really care about coefficients at all. How we assess the models is very different. It's all about selecting between different models using these kind of performance measures. And then at the end, what we care about is being able to predict, right? Now, having said all that, like I said, you should be cautious when using these models. You should be especially cautious when using models that you don't understand how it's working. But in general, these are powerful tools. And you should, at the very least, if you don't remember anything about the coding, just remember machine learning predicts well. If you have decision-making that requires good prediction as an input, then machine learning is what you want. If not, then causal analysis is probably what you want. All right. So having said all that, I'll reiterate once again, this is not going to be tested on the final exam. But I hope that you found it interesting, and I hope that it serves you well at some future job or future juncture. So that's it. Take care.